Recording is rolling. It is Wednesday, December 11. All right, so actually, we're going to start with the quiz you guys took yesterday on energy and momentum. So, uh, almost everybody took. I still have a couple of students from each class that have to take this. So, hang tight on that. I do want to get those back to you guys as soon as I can. Right. So, top scientists. So, if you see your name on one of these top scientist lists, you're really awesome. Here's for my AP students. All right. AP top scientist. Here's my conceptual students, top scientists. And so I have one class of each of those. And then I have four honors classes. So here's my top scientist for all my honors classes. And I have three students in all my classes who scored a perfect 100. That's Hughen, Carson, and Elise. So all honor students scored perfect 100. So awesome job if you are top scientists. All right. And so after everybody takes that, then I will get that back to you guys the following day, and then you guys can do corrections. So corrections, same story as it's been all semester. If you just write the correct answers to the ones you missed and turn that in, I'll give you partial credit back. So there's two main types of questions. There were these conceptual questions, and probably the best you can really do is just write out the correct sentence. So you can do that way. Right. But a lot of these were puzzle questions that you could solve with equations. Is if it's one of those, you have to set up the correct equation and then get to the answer. If you just write like, oh, the answer is equal to 4 or something like that, that's I'm not going to give credit for that. Right. So if it's something you have to solve with an equation, set up the equation, solve it that way, and then I'll give you credit back for that. Right. Right. So today we're going to do midterm review. Actually, today and next few days. So do you guys remember the study guide page I gave you? What? Oh yeah. Well, just before you leave for the break. Yeah. Yeah. Right. So yeah, so I have to get all the quizzes back in first, and then I'll go back to you guys, and then yeah, just I think you guys should be able to get this back in before the break, and then I'll get all the points into the book. Okay. And so the study guide page, we're gonna do a Kahoot today, and then also tomorrow and the next day that covers each one of these questions one by one. Right. So the midterm is going to be open notes. So any notes you guys have been taking this semester, you guys can use. The study guide page will count this as notes. Any papers that I printed to give to you that you write on, this can be notes. So any materials from this class can all be notes. It's going to be in two halves. So the first half is going to be 50 multiple choice conceptual questions, which come straight off the study guide. And we're going to go over the answers one by one with Kahoot today. Okay. The second half is going to be 10 puzzle questions that are equation based and solve with equations. It's going to look a lot like some of those puzzle questions from yesterday's quiz. It's kind of like that, except these will be for the entire semester, like 1 or 2 questions per section for the entire semester. Okay. Okay. And then you guys have a show and tell opportunity this Friday. All right. You guys got any questions about anything on? All right. Let's go over to Kahoot. Oh, yeah. You guys are logged on, ready to go. Depends on the board. All right. Does anybody need a study guide before I get rolling on this? Need a study guide? If you do, here, there's a stack of them right here. All right, so you can get one if you don't have one. If you do have it out, then you guys know we're going over these one by one. All right, here we go. Well, it's 105 questions, but that aside, modify this a little bit. When you look at the speedometer of a moving car, instantaneous speed, how fast are you going at that instant? The speedometer needle points to how fast you're going, instantaneous speed. Okay. Now, if that speedometer needle is moving, you could calculate the acceleration. You say, well, it moved so far and so much time, so that you could calculate that, but that's not what it points to. Right? And then distance is the odometer. Right? Average speed is like total distance over total time, which we hardly ever talk about in this class. Like you guys know those 3 kinematic formulas that keep coming up over and over in this class? Every time you see a V, is that referring to an average or an instantaneous value? Yeah, instantaneous. Yeah. Okay. So how fast are you going that instant? Right? If you have questions on any of these, just stop me, let me know, and I can fill in some details. Right? Train travels 7 meters, then 7 meters, then 7 meters. So like each second. What's the acceleration? 0 meters per second squared. So you could say the velocity could be 7 meters per second. It's going 7 meters every second, every second. But acceleration, well, linear acceleration has to do with speeding up and slowing down. But it's anything constant velocity is 0 meters per second squared, 0 acceleration. I got Zariana, Olivia, Elise, Alexander, Isabel. Car starts from rest. After 7 seconds, picks up to 42 meters per second. What's the acceleration? At 6 meters per second squared. So if you start from rest, the velocity you pick up to is just acceleration times time. So 6 times 7 is 42. All right, 6 times 7 is 42. All right. As an object falls freely in a vacuum, it's yeah, velocity increases, right? So okay, I know every time it shows the answer, it gets rid of that poster picture, that graphic. But I had that table there. If you guys have your thumbnail notes out, then you can see that too. If you drop something from rest at the edge of a cliff, does it pick up every second goes like 10, 20, 30, 40, 50 meters per second, right? Picks up 10 meters per second every second. So the velocity is increasing, right? Now the velocity is increasing at a constant rate. Guys, what's the rate change in velocity called? Acceleration, right? And that should be a constant value, right? So acceleration is constant, velocity is increasing, right? In a vacuum. All right, got Isabel, Zariana, Olivia, Alexander, Elise. In the absence of air resistance, objects fall at constant. Slash graph right here. Yeah, constant acceleration. And on Earth, that would be 9.8 meters per second squared. And a lot of times we'll round that to about 10 meters per second squared. That's a constant value. So it picks up velocity at a constant rate. All right. Suppose an object is in free fall. Each second the object falls. Yeah, a larger distance than the previous second. I know if I go to the edge of a cliff and drop a ball, in the first second, it's going to fall 5 meters. And the next second, it falls all the way down to 20 meters. So it picks up an additional 15, right? 5 plus 15 gets you to 20. The third second, it goes all the way to 45 meters. So that's 25 meters more. So every second, it's falling further than the previous second because it's speeding up. All right, Peyton, Olivia, Isabel, Elise, Alexander. Ball tossed vertically upward, rises, reaches highest point, falls. During this time, acceleration is directed downward. Is which way does gravity pull? Straight down. Okay. So there's velocity, acceleration, two different concepts. Velocity is like how fast it's moving and also which direction it's moving. Okay. So if you throw the ball up, yeah, at some point it's moving up and then later on it's moving down, but those are velocity concepts. Acceleration has to do with the direction that gravity's pulling, right? The gravity field is downward. Right? It's always accelerating downward, right? Slows down on the way up, speeds up on the way down. Okay. You guys good with all these so far? Is that right? Right. All right. We got Zach, Olivia, Isabel, Elise, Alexander. Ball thrown straight up. At the top of its path, its instantaneous speed is 0 meters per second. All right. 0 at the top. Okay. Sometimes you open up a physics textbook, it says you throw a ball straight up at some speed. How high does it go? And if you want to run an equation, you have to remember this fact right here. Say, oh yeah, well, I do know at the top it is 0 meters per second. Right. And then that gives you the last numerical value you need to be able to solve the equation. All right. Look at that. Ball thrown straight up. At the top of its path, its acceleration is 10 meters per second squared, right? So isn't it true from the moment right after you release the ball until right before it hits the ground, it's always accelerating down at 10 meters per second squared, including the very top where it's turning around. It's just in free fall, right? So the entire time it's in free fall, right? 10 meters per second squared down. All right, Luciana, Peyton, Elise, Alexander, Isabel. Car accelerates 2 meters per second squared. Starts from rest. How much time to get up to 20 meters per second? So you guys got 2 times 10 is 20, right? So 2 meters per second squared times 10 seconds gets you to 20 meters per second. So second kinematic formula. All right. Freely falling object. Its speed would increase each second by picking up 10 meters per second every second. Yeah, there you go. 10, 20, 30, 40, 50. Yeah, Olivia, Peyton, Elise, Isabel, Alexander. Freely falling object starts from rest after falling for 2 seconds is to a speed of about so G times T. All right, so 10 meters per second squared times 2 seconds gets up to 20 meters per second. Right? No, suppose this question comes up on the midterm. Is it okay if the time changes? Like, what if it was 5 seconds? You guys could solve that, right? You say, oh, 5 times 10 is 50. Like, 10 times 5 is 50. All right. Ball thrown to the air at some angle. At the very top of the ball's path, its velocity is it should be entirely horizontal, right? Entirely horizontal at the very top, right? So the vertical component goes to 0 at the very top, but horizontally it's just going across the same way, same horizontal component of velocity all the way across. All right. A ball thrown will never go as far as physics ideally would predict. Like we could solve it with an equation. Why? And look for air friction. Right. Here's what. We could solve projectiles on paper. Right? You say, well, okay, if I throw it this speed at this angle, give it a velocity, Earth gravity, I can say, all right, it looks like it's going to land like 50 meters downfield. And then we could go back behind the school and start throwing a bunch of tennis balls with those exact conditions. And they'll always land a little bit short. It's like, well, why is it only landing like 45 meters or 40 meters? Why is it not going the full 50 meters? Oh, well, I accounted for velocity in my equations. I accounted for gravity in my equations, but I didn't account for the air drag. And that's the realistic um, variable that we usually ignore because it makes the math like crazy complicated. All right, got Zach, Isabel, Alexander, Peyton, Elise. Absence of air friction. The horizontal component of a projectile's velocity does not change. 40, 40, 40, 40, 40, 40, 40 meters per second. That's true, right? So, yeah, so horizontal component of velocity, as long as there's no air drag. Right. Now, I know the overall velocity changing, the vertical component of velocity is changing because gravity pulls vertically. Right? But if there's no horizontal force, it's just going to post horizontally. All right. Zach, Isabel, Peyton, Alexander, Elise. Same time, one ball's thrown horizontally, one ball's dropped from the same height. Which reaches the ground first? Drop, one thrown horizontally. Yeah, same time, same time. They have the same vertical motion. Right? They'll hit the ground at the same time. Same vertical motion. All right. Airplane flying 40 meters per second north enters a 30 meter per second eastward crosswind. What is the plane's ground speed? All right, so looking for 50 meters per second. There's been a couple questions been thrown students all day today, and this is one of them. So I'm gonna switch over here and solve this with you guys. All right, just here. So I got a plane. Okay, let's say it's pointed straight north. Hey, guy's trying to fly straight north. It's going at 40 meters per second. Okay, guys, did I just draw a free body diagram? Yes or no? No, because a free body diagram only has what type of vectors on it? Force vectors, right? Or torques later on. Okay. But this is a what kind of vector? Velocity vector, right? Okay. Now this plane's going to enter a crosswind that's blowing straight east. Okay. It's blowing east everywhere. So if I connect two velocity vectors, how do you connect vectors? What to what? Tip to tail. So I'm going to go to the tip of this one, to the tail of the next vector. This is your crosswind right here at 30 meters per second. Is that okay? Now, if you go from the tail of the first vector to the tip of the last one, you'll get the resultant vector, and it'll tell you exactly what the plane's doing. Now, this is only 2 vectors. If you had 10 vectors, you could chain them all like this. You still go from the tail of the first to the tip of the last. Right? Here's the resultant vector right here, the resultant. I'm going to write that down. Resultant vector. Right. This is so here's the plane relative to the air. Here's the air relative to the ground. Therefore, here's the plane relative to the ground. Right? So what that is? Right? And guys, that's how fast? Or how would you figure out how fast? Suppose these were crazy different numbers. Square root of a squared plus b squared. Right, like that. So this would be meters per second. Okay. And it comes out to 50 meters per second. Because guys, this happens to be a what triangle? 3, 4, 5. So 3, 4, 5 proportional triangle, right? Okay. You guys see that? Okay. I think the question on your paper is phrased like something like the ground speed would be faster than the original speed of the plane, something like that. Okay. We got one more question here though, okay, which is what direction is the plane actually moving? Because the plane's pointed north, but it's not actually moving north. It's kind of going northeastish. Okay. How do you figure out what this angle is right here? You have to do what? Inverse tan, yeah. So if you know the sides of a triangle, we know all 3 sides, 30, 40, 50. You want to figure out the angle? Yeah, you have to play an inverse trig. I'll do inverse tan. Now, if you do inverse tan, you're playing off which 2 legs? What divided by what? 30 over 40, right? 30 over 40. And what does that come out to? That 37 degrees east of north, right? Could be the bearing. Okay. Bet that is. I got Olivia, Peyton, Isabel, Alexander, Elise. What's the resultant of 3-unit and 4-unit vector at right angles? That'd be 5 units. So that'd be a 3, 4, 5 triangle right there. If the numbers were any different, you could just do Pythagorean theorem. So 9 plus 16 is 25, square root. Oh, it's 5. Aha. All right. When in orbit, a satellite such as the space shuttle is for simply a projectile, right? And so first of all, why is it not these other ones? Because isn't Earth's gravity the force that's acting as the centripetal force that's keeping it in orbit, right? Which means it's also accelerating. It's a centripetal type acceleration, right? Now, when we were solving projectiles back in the day, normally like locally, if you keep projectiles like within the state of Florida, then it's like, yeah, that's pretty flat, sort of, right? But if you have something in orbit, you have to consider the curvature of the planet. This satellite in orbit is going so fast, it's actually falling around the curvature of the Earth. So projectile around the curvature of the Earth. All right. Law of inertia. Yeah, there you go. Object rest, state rest. Object motion wants to move in a straight line at constant speed. It's called constant velocity. Yeah. Until there's an external force. So all the above. It's all parts of law of inertia, Newton's first law of motion. All right. Ooh, what's going on here? Ah. Cannonball fired into space. The amount of force required to keep going. Or how about Voyager spacecraft? How much force is required to keep that spacecraft going? Been going since the 1970s. How much force keep going? 0 newtons, 0 newtons, right? Like anything in space, it's a really good place to think about fundamental physics. Right? So, how about the Earth? The Earth is orbiting around the sun. Is the Earth going to like slow down and fall into the sun? Or is it just going? Inertia is keeping it going, right? Inertia. So no force required. No force. Yeah, Zach, Peyton, Isabel, Alexander, Elise. If the force of gravity suddenly stopped acting on the planets, they would. Here, the colors match. Which color? Yeah, move a straight line tangent to the orbit. Okay, since my picture went away, let me go over here and actually here, got a good picture right here. Okay, so it could be the sun, the Earth's going around. If you suddenly turn off gravity right here, the answer is, well, here's the velocity, the instantaneous velocity, and it wants to just keep doing that, following the law of inertia right there. Tangent, if something's tangent to curve, that means you can take your ruler and put it flush to the curve, and that's the direction it's going to go. Ooh, here's what if I change the story a little bit? What if this is a ball on a string and you're at the middle wheeling this around your head, and then you let go right here? Does the ball fly straight away from you, or does it fly tangent to that motion? How about tangent to that motion? It's the same answer. Right? It's still a law of inertia. Zach, Alexander, Isabel, Peyton, Elise. Sheet of paper can be withdrawn under a container of milk without toppling it if the paper is jerked quickly because. Yeah, inertia. Inertia. Right, just wants to sit right there. Got lots of inertia. Zach, Alexander, Elise, Isabel, Peyton. The force required to maintain an object constant speed in space. No force. 0 newtons. No force. You're out in space, you're just going. You guys remember that free body diagram for a rocket at constant velocity in deep space? There were no forces. Right? It was just going. All right. Acceleration is defined as change in velocity over change in time. So what's the rate change in velocity? So this is linear acceleration. How much are you speeding up or slowing down? Change in velocity over change in time, right? Now, I remember this was a bridge variable between kinematic and dynamic motion. This is a kinematic perspective, right? So acceleration is rate change in velocity, right? The other side of this, the dynamic side, was Newton's second law of motion, which I think this is about to, it's about to bridge over to Newton's second law of motion. We're about to be looking at real soon right here. Acceleration produced by a net force is, there's Newton's second law. Yeah, all those are true. Right, so acceleration directly proportional to the net force. So guys, if you double the net force, are you also doubling the acceleration? Yep, that's what directly proportional is. Okay. Same direction as the net force. If an object has like 10 different forces on it, first thing you do is find out what's the net force as if it was a single force. And then the acceleration is just in the same direction. Okay. And then, ooh, guys, how about this? Suppose you have a tennis ball versus a bowling ball, and you kick both of them with the same force. Tennis ball versus bowling ball. Which one is going to accelerate more? The little tiny tennis ball. That big old bowling ball might be below it, but hardly at all. Because the bowling ball has so much mass, the acceleration is really small. And that's an inverse relationship between mass and acceleration, right? Like F equals ma, A equals F over m. I got Zach, Alexander, Elise, Isabel, Peyton. Equilibrium. Yeah, all the above. So the forces zero out, the net force is equal to zero. If you introduce a Cartesian system, x and y axes, or even x, y, z axes, and look along each axis, the forces still zero out along each axis. You guys see this gold one right here? The net torque is equal to zero. We barely talked about that at all, but you guys have all probably used a wrench at some point, right? So radial arm crossed with the force going perpendicular, that'll give you a torque, a turning moment. If you ever open a door, you're providing a torque, right? That also zeroes out. If anybody's going into civil engineering, maybe you're going to design some large static structures. What you're looking at right here, this screen, is your conditions for building a static structure. Okay? You just have to make the forces sum to zero in each direction and the torque sums to zero, and then you can solve for everything. All right. Zach, Peyton, Alexander, Elise, Isabel. Suppose you weigh 500 newtons hanging in the middle of a bar supported by two vertical ropes. What's the tension in each rope? So you're hanging right in the middle, 500 newtons. What's the tension in each one of these ropes? Yeah, there you go. 250, 250. Right, you guys see that? Right. Now, probably in January, we're going to address the question, what if you're not hanging right at the middle? Because what if you're hanging like 3/4 off from the end? Do you think the tensions still add up to your weight? Yeah. But do you think they're the same anymore? All right, so that'll be January. Right. All right. Friction. Always opposite of the motion. Opposite of the motion. Friction is always opposite of the motion. Right? Right. So if you're dragging a block across the surface, friction is the opposite way, trying to slow it down. Right. Here, give you guys a kind of a tricky version of this. Here, guys, suppose your car starts from rest. Let's do a car example. And you put the car in drive and start driving. What force is propelling the car forward? Is that friction between the tires and the road? Right? Now, from the point of view of the wheel's turning. Now, if the wheel was like stuck in the mud, just spinning in place, you guys think the bottom of the wheel is actually kind of moving backwards of how the car's trying to move? Ah, that's why friction still propels the car forward. Right? It's a little tricky version. All right. Zach, Peyton, Alexander, Isabel, Elise. What's the maximum possible resultant from 2 newtons and 8 newtons? Ten newtons. It's just in the same direction. So if you push forward with 8 newtons and your friend pushes forward with 2 newtons, the collective force is 10 newtons. That's all. Right? Because what if they were pushing opposite of each other? What would the net force be? It'd be 6, right? Because 8 plus -2 could be 6, right? Because what if you're pushing perpendicular? Could you apply a Pythagorean theorem and solve it that way? Right? All right. What's the tension in each rope? So I have a 100 Newton lantern pulling straight down. Got 120 degrees between each rope. Pair of ropes. What's the tension in each rope? Ooh, 3 winners, which is pretty good because this is one of those other questions that's been throwing students all day. So let's get a close look at this one. Let's look here. So let's get a Cartesian system going, get a vertical axis, horizontal axis. Okay. Now we just made up the axes, but we're going to use this to break some vectors into components and make sense of this. So you guys see this big old dot right at the origin? That's where all the ropes are going to come together. So I got one rope that's definitely straight down and have a 100 Newton tension force. So I'll say tension equals 100 Newtons straight down because the weight of the lantern is 100 Newtons. Okay. Then I got these ropes. I got one up to the left and one up to the right. Okay, I don't know if this is 100% exactly to scale, but probably pretty close. Okay. So that if I drew this right, this angle is 120 degrees, this angle is 120 degrees, and this is 120 degrees. Okay. Okay. Guys, what is 120 plus 120 plus 120? 360, which is the full circle, right? Okay. Okay. So relative to the vertical, what is this angle right here? 60. 60 degrees. Oh, and this would be 60 degrees. Okay. What is this angle right here? Huh? Or how about this angle right here? How much? 30 degrees. 30. Okay. You guys get so far? Right. So let's look in terms of components. Let's say I don't know what this tension is yet, or what is this tension? Although maybe by symmetry, I can kind of figure that bit. But let's do a component analysis. I know that each of these tensions is pulling horizontally some amount. Left versus right. And each of these tensions is pulling straight up. Well, not straight, but there is an upper component, I should say, right? Upper component. Okay, guys, yeah. Right. Good so far? Right. Okay. Now, if the lantern weighs 100 newtons, right? Lantern's 100 newtons. How much collectively do the tensions have to pull up? 100 newtons. Which means that this component right here is equal to how much? 50 newtons. Isn't this right here? 50 newtons. And I guess this would also be 50 newtons. Do you guys see 50 and 50 up? Balances with 100 down. I see that? Right? Right, guys good? Yeah. Guys, look at this 30-degree angle. A 30-degree angle is a really nice angle to work with in trigonometry. Okay. Because if my ultimate goal is to figure out this tension, isn't that like the hypotenuse of a right triangle? Okay, so I want to find the hypotenuse and solve for this tension, maybe. I know the leg opposite of the known angle. Okay. Guys, what relationship do these two sides of a triangle have with each other relative to this angle? Is that sine, cosine, or tangent? Sine. Yeah. So I'll set up a fraction here. I'll say sine of 30 degrees. I'm going to like a math book definition version. Is opposite over hypotenuse. That's 50 newtons divided by the tension. Okay, cross multiply tension, divide down sine of 30 degrees. Actually, you know what? Sine of 30 degrees, I think you guys should know this one. What is sine of 30 degrees? Is how much? 0.5. Yeah, it's exactly 1/2. That's a good one to know. Right? So if you have a 30-degree angle and a right triangle, then the short leg compared to the hypotenuse is always a 1:2 ratio. Right? So no matter how you do it, you're gonna get tension is 100 newtons. You guys see that? 100 newtons right there. Right? You guys see that? Let's do a little bit more with this. So does anybody know for a 30-degree angle triangle? Well, this angle up here, let's hit this again. Guys, what angle is this right here? 60 degrees. So let's call that a 30, 60, 90 triangle, right? 30 degrees, 60 degrees, 90 degrees, right? What are the ratios of the legs? 1 to 2 to square root of 3. That's a good fact to shuffle away, right? So 1 to 2 to square root of 3 ratio, right? So if I do 50 times the root of 3, or I could have gone through cosine or whatever, but this comes out to 86.6 newtons this way, okay? And this one here is 86.6 newtons to the left, right? Get that? Right. Last thing, actually, what you could have maybe solved this whole thing with more simply is radial symmetry. The fact that all these angles between the ropes were the same, 120, 120, 120 degrees, means that the tensions had to be the same from the outset anyway. So if you know one of them is 100 newtons, they all had to be 100 newtons just from radial symmetry. All right. So you guys good on the lantern question? And lanterns. All right. There's some vector analysis right there. All right. We got Alexander, Zach, Elise, Peyton, Isabel, and points. Ooh, tight race. Which has more mass? Yeah, same mass. They're both 1 kilogram. 1 kilogram is 1 kilogram. All right, guys got 1 kilogram is 1 kilogram. Accelerations come from look for forces. So remember, you have two perspectives on acceleration. The first perspective is, well, acceleration is a rate change of velocity. That was kinematic. The new perspective is what causes accelerations are forces acting on masses, and that's Newton's second law of motion. I know my graphic went away, but that was that bridge variable, wasn't it? Acceleration is a bridge between kinematic and dynamic motion. So forces acting on masses. Guys, if there were no forces, would there ever be any accelerations? No, you need forces to get accelerations. No forces, no accelerations. All right, Alexander, Peyton, Isabel, Zach, Elise. Woo! All 18,000 up here. Look at that. Ooh, that's close, right? How does acceleration change in relation to mass? Like if there's more mass. That's a looking for an inverse relationship. Here, guys, inverse relationship. Here. Got a small mass and a big mass. You guys see a small mass and a big mass? Right? Guys, could this be maybe a tennis ball versus a bowling ball? Right? Here. What if I push each of these with the same force? Same force. Which one's going to accelerate more? Let's do the same force on each of these. Force on this guy. Force on this guy. Ugh. You guys see? Here, let me write down Newton's second law of motion. Acceleration is a net force acting on a mass. Right? I think each of these objects had 3 forces on them. Has the weight down, the normal force up, those just balance out. But really my applied force, my pushing force. Right? So, so the more mass you have, the less the acceleration for a given force. That's Newton's second law of motion. When an object reaches terminal velocity, its acceleration. Yeah, 0 meters per second squared. Ooh, guys, to reach terminal velocity, you have to have what that we usually ignore in this class? Air drag. Yeah, air drag, air friction, air resistance. Yeah. Can you reach terminal velocity in a vacuum? No, I don't think so. Because in a vacuum, it just always speed up. Right? Okay, so you need air drag to reach terminal velocity. Then you reach zero net force. Maybe the weight is balanced out by the air drag. So zero acceleration. Alexander, Peyton, Isabel, Zach, Elise. Ooh, we're at 19,000 territory. Ooh, anybody could get the gold. Book weighs 4 newtons. When at rest in your hand, the net force on the book is? For 0 newtons. Is what's the net force of anything at rest? 0 newtons. Anything at rest, 0 newtons net force. Unless you talk to Einstein with general relativity, but we're going to stick to Newtonian mechanics here. 0 net force, 0 acceleration. At rest, the example. Got Peyton, Isabel, Zach, Elise, Alexander. Woo. There's got 19,000 points. Pull 10-kilogram wagon with 20 newtons force. What's the acceleration? 20 newtons acting on 10 kilograms. Guess what's 20 newtons acting on 10 kilograms? 2 meters per second squared. Newtons over kilograms, same thing as meters per second squared. So 20 divided by 10. Oh, you guys picked the rocket answer. A constant force produces a constant. Acceleration. F equals ma. Newton's second law of motion. Constant net force produces a constant acceleration. Got Isabel, Peyton, Alexander, Elise, Zach. Suppose the friction force on a sliding object 35 newtons. The force required to maintain a constant velocity, let's say the applied force. Got 35 newtons friction force. What do I need on the applied force? Yeah, 35 newtons the other way, right? So 35 minus 35. Okay, so, maybe I need to amend this because if you pick the red one, the red one actually is the net force, isn't it? The red one's the net force, but I was looking for the applied force. Okay. All right. All right. Ooh, Isabel, Peyton, Zach, Alexander, Elise, and we got one question left, and anybody can win. You guys ready for the win? Who's gonna win? And Minnie throws one rock, drops another. Now, after the rock leaves her hand, the acceleration is after the rock leaves her hand. Same acceleration because it's just the gravity field, right? Once the rock's left your hand, it's in free fall. It's the same acceleration. Ooh, all right, you guys ready for podium? Podium time. With the bronze, Alexander. The silver, Peyton. And the gold, Elise. All right, nice job, guys. I say good job. You guys are getting ready for this midterm. All right, we're gonna do one puzzle here. Let's do an Atwood. You guys ready for an Atwood? Atwood time. Let's do a classic Atwood. We got a pulley, massless, frictionless pulley, and a couple of blocks here. Let's say the mass of this guy is, say 3 kilograms. Let's say the mass of this guy is, how about 5 kilograms. 5 or 6. Okay. All right, so bunch of questions. Probably the go-to question is what's the acceleration, right? Like what's the downward acceleration of the large block? It might be phrased, right? You could ask what's the tension in the string. You could ask kinematic questions like how far has it moved after so much time. Let's see how far we get. Right. Now, there's different ways to approach this, and if you take physics in college, they might start a little bit different way. They might start a system of equations. Oh yeah, good. There you go. So I'm going to walk you guys through like I normally do. So I'll do a whole system approach. So let's throw some forces on here. Guys, what is this weight right here equal to? Huh? How many newtons? 50 newtons. 50 Newton weight right there. Right? And what's this weight equal to right here? 30 newtons. So we're going to assume we're on Earth. That's good implication. So we're on Earth. Okay. Oh. So if you're considering clockwise versus counterclockwise, what's the net force? Net force on total mass, I know would give me the acceleration. And I'm considering clockwise versus counterclockwise. You guys see 50 newtons minus 30 newtons would give you the net force clockwise versus counterclockwise. Mm-hmm. Okay. And how much total mass is being moved around? 8 kilograms. Okay, because I got 5 kilograms there plus 3 kilograms there. That 20 newtons net force on 8 kilograms. Like 2.5. Ooh, guys, Newton over kilogram. That's also called what? Newton over kilogram. Meters per second squared. It's the same thing. I know. I tell my AP students to watch for that on multiple choice because AP likes to do that, especially for gravitational fields. They like to use Newton per kilogram. So, anyway, so here's the downward acceleration of the large block or the upward acceleration of the small block. Guys do that. All right. Let's do those follow-up questions that I was asking you guys. Could you guys solve for tension? Like if we go back and complete this free body diagram, you guys think there's some tension force here? Yeah, we'll call it capital T. Right? Guys, is this tension, is that the same tension? Yeah, as long as this pulley is massless frictionless, that'd be true. Maybe the pulley is locked in place. Like this. Right. How about, does the tension have to be more than 30 newtons, but also less than 50 newtons? Right? Like the Goldilocks type force? Right? Because I know the large block has to accelerate down, the small block has to accelerate up. So the net forces also have to be those ways. Okay. Let's figure out what those tension forces are. Right. Now here, I'm either going to focus on one block or the other block, just individually. Can I do net force equals mass times acceleration for a single block? Right. And net force, let's say I pick the big block. Can I do tension up? Or no, let's do it the other way, because it would be accelerating down. Let's do 50 newtons down minus the tension up would be the net force. And that's a 5 kilogram block, so 5 kg, accelerating at, how much is it accelerating? 2.5 meters per second squared. We just found that. So 2.5 meters per second squared. Times for 5, about 12.5 right there. Add that, subtract that. Tension is whatever 50 minus 12.5 is. All right, I think it's like that right there. That's it. What if I had done it from the perspective of the small block? Would I get the same tension, do you think? See if I do. So here I'll do net force equals mass times acceleration for the small block. Let's do tension up minus the weight down causes this block to accelerate at also 2.5 meters per second squared. This is like 7.5 plus 30. Yeah, it's the same thing. It's the same thing. Right, that's it. Either way. Okay. How about let's do a kinematic question. Okay. So Here, I'll just set these up. If I ask you guys, how far does this move after some time, like 1 second? Could you guys figure that out? Guess what formula would you use to answer how far does it fall after so much time? X equals what? Let's say it starts from rest. 1/2 AT squared, right? Here's your acceleration point. So if it gave you like 1 second, could you plug in 1 second here and then solve for how far it fell? Suppose I asked you guys, how fast is it moving after some amount of time? After 1 second, how fast is it going? What formula would you use? D equals what? AT, right? And then same acceleration. You just point, pop that in right there. So after 1 second, I know we'd be going 2.5 meters per second. Do that. Okay. And the third kinematic question I could ask you is, how fast is it moving after some distance move? Now that one, you guys remember that third kinematic formula? Goes v squared equals v naught squared plus 2ax. Now if this starts from rest, like these other ones do, this one just goes away. Okay. Here's your acceleration point. Okay. Now suppose the distance move was like 0.40 meters. So you plug that in there for x, and then you could solve for, well, you'd have to take a square root at the end, wouldn't you? And solve for that. Okay. So there's 3 kinematic questions I could ask. Right, you guys do that? Okay. Oh, speaking of kinematic, I always have this poster on the side ready to go. You guys remember these kinematic foremost? But we kind of just applied this, didn't we? All right. All right, so I think that is a good pause point today.